they can sit, so even more comfortable in this way. Well, now I found a solution for the technical problem, and we can start. As you see, the title is Single Fibers as a Tool in Aging Muscle Research, but I thought to start a bit from an enlarged view and then going down to the micro level, to the cellular level of the single fiber. So if we search in the website of WHO a definition for aging, we find something that aging is defined as a gradual decrease in physical and mental capacity, a growing risk of disease, and ultimately death. Well, a rather, pessimistic view of anyway, it corresponds to the idea that life is based on two phases. First we go up, we improve ourselves, and then we go down, and this is the aging phase. In a way, this pessimistic view corresponds to the old sentence, senectus ipsa morbus est, aging is disease in itself, which was written more than 2,000 years ago by Publius Terentius Afer, was a writer in Latin from North Africa. Actually, Publius Terentius died rather young, so for him it was not possible to understand, to experience what was really aging. And the pessimistic view came from observing other people. But also at that time, not everybody shared this pessimistic view. For example, Cicero wrote a book about aging, De Senectute, and in this book we can find some, positive or a bit less negative view about aging. For example, the sentence, omnia autem quae secundum natura fiunt, sunt abenda in bonis, translated in English means that everything, all things which are according to nature, follow the nature rules, are good, can be accounted for good. So also aging must have something good if nature has organized the life in this way. And another, optimistic sentence is, to me, this one. Nemo enim est tam senex qui se annum non potet posse vivere. No one is so old that cannot imagine to go on at least another year in his life. This is just the beginning of the reflection about aging thousands of years ago. But our point of view is not just to reflect if it's good or not good. As scientists, we try to understand what is aging, measure something, quantify this decline, this loss of function, this worsening of the body, deterioration, but quantify, measure, understand the mechanism, maybe going down to cellular and molecular level, and possibly find something which, avoid aging, but at least delay, postpone, following what we can call as a final aim, healthy aging, aging in good health that allows to keep acceptable style of life. All organs, all tissue of the body undergo to this aging process. What is in our interest is the muscle, and the muscle is rather important for the aging process because if our muscles, skeletal muscle, don't work well, we lose mobility. So we are not able to walk inside the house, go to the kitchen, go to the bathroom. We are not able to go out, climb the stairs. So it's an important part, the decline of the muscle during aging. And this decline of the muscle has two main aspects, very easy to identify, to see just by eye. Of course, we are dressed, but if we take out our clothes and we look at our legs, we can see how the legs of the elderly people become thinner. So there is atrophy, loss of muscle mass, and at the same time, loss of strength, power, weakness of the muscle. These two aspects have been measured during the last decades many times in very nice studies. I just selected 3 of these studies to give some kind of frame inside which we can put our single fiber studies. This, for example, is one of the studies where many people, hundreds of people were of different ages, so it's a transversal study. At the same time, many people of different age, from 45 to 85, has been measured in the size of their muscle. Men and women, upper limb, lower limb. Populated with straight line, which show a continuous, more or less linear decrease of the muscle mass, more pronounced in men than in women, and more pronounced in the lower limb than in the upper limb. Approximately 0.51% of the muscle mass is lost every year. So over 20 kilo, 1% means 200 grams. About the performance, the strength and the power, there are also many studies. I selected among them one which to me seems very nice. I was always liked this study. In the occasion of the World Master Championship of Weightlifters in Glasgow, 1999, more than 100 athletes accepted to measure not the ability to weight, to lift, to move the weight, to lift the weight, but to measure in an ergometer, in an explosive ergometer, the peak power. And a similar number of sedentary controlled people, with the same age distribution, more or less underwent the same test. The diagram showed that there is, for both the weightlifters, athletes, and the sedentary control, the same trend. The peak power decreased more or less linearly over the age. Again, we are in the range between 40 and 85 years. And the decline is more or less the same in athletes and in controls. Of course, there is a big difference that for each age group, the trained people, the athletes, are better, perform better than the control. So this indicates that no training can avoid the decline. What we can expect is that the train postpones somewhat the decline. So at the same age you can keep a better performance. This decline of the performance of the weightlifters was taken up again some years later in a review article by John Faulkner. This is see if I can use this is a pointer without destroying everything. Was used as reported as an indication of the decline in this review article by John Faulkner, and these are the empty circles, this line. These are the average for different age groups of the weightlifter. Then John Faulkner added to this also the decline of the better performance of the marathon runners, senior athletes. Also this shows a decline. But in the case of the marathon runner, in reality the limiting factor is the cardiopulmonary performance more than the muscle performance. While for the weightlifters, it's really the muscle performance which declines and causes this loss of performance. Then, last study I want to mention, a longitudinal study. Longitudinal study, more than 2,000 people started, and then almost 2,000 arrived to the end of a 3 years period where these people were measured repeatedly during these 3 years to control their change in their muscle mass and their muscle strength. Men and women, black and white, of course, this can be considered a bit, a bit racistic to divide, because in reality they are not very different. If we compare white and black women, it's just the same, but anyway, it was organized in this way. And what we can see in 3 years, starting from 74 years to 77, they lose something like 1% of the muscle mass per year, as more or less as expected, and they lost 3 times more strength, measured with an isokinetic knee extension and isometric condition. So this indicates that there is also qualitative change. Not only the muscle becomes smaller and for this reason less strength is produced, but also the ability to develop stress force is reduced by the aging. No? There is a qualitative. No? So correctly in the title they speak about loss of strength, mass and quality. To say that they started at 74 years is rather not just by chance, no? Because there is some indication that the aging process is not a linear continuous process, but there is some kind of acceleration of the deterioration of the muscle. And there are several ways to classify the aging process, for example, divided in 3 phases. The first phase, the phase of the older adults, or youngest old, between 75 and 74 years. Then there is the phase of the old or middle old, 75 to 84, and then there is the phase of the oldest old, above 85, until the possible end at 120. 120 is considered the maximum human longevity. Well, the changes which occur in this period, in these, say, 30, 40 years, are the results of many different factors. Also for this there are many graphical representations of these changes, but you see that here is mentioned, for example, endocrine factors, not the decrease of the circulating level of hormones like androgen, estrogen, which are anabolic effect, of course, is responsible for some atrophy of the muscle as of other organs. Then there is the change in lifestyle, physical inactivity, change in nutrition. Then there is definitely the aging of the nervous system, and particularly the death of the motor neuron. Then there is the chronic inflammatory condition typical of the elderly people. And then there are intrinsic changes in the cell present in the muscle, cellular changes and, so to say, metabolic changes. Well, to understand, to put a bit in order and discuss this factor, I try to identify 3 main components which could be considered as responsible of the decline of the performance and the mass of the muscle during aging. The first point to consider is that elderly people are still able to activate their muscle. I mean, if it's not the aging of the brain responsible, this voluntary activation can be checked, controlled with some rather easy and rather reliable technique like the interpolated twitch technique, where we compare the effect of the electrical stimulation of the muscle and the voluntary activation. Well, the indication is that there is a little component, but very little, definitely not sufficient to explain the loss of performance of the muscle. Then a second component is the death of the motor neuron. Motor neuron die progressively as all neurons die, no? But the loss of the motor neuron has a big impact on the muscle, because the fiber innervated remain without drive, like neural drive. Either they are reinnervated by adjacent motor units, or remains innervated and slowly die. This factor is definitely present, has been described very well starting 40 years ago by Lexell and his co-workers in Sweden. They counted in autoptic studies the fibers in the muscle, and they described this decline of the number of the fibers related to the decline of the number of motor neurons, and can be, in living people, estimated, followed in some way with refined electromyographic study, which allow to estimate the number of motor units present in a muscle. And then the third component is, the intrinsic change of the muscle fiber. In the muscle, there are many different cell types. There are, of course, the typical cell type, which are the muscle fibers, but then there are fibroblasts, adipocytes, inflammatory cells, and many, many types. Single fibers can be identified, take out from the rest of the muscle, studied, and this can allow us to identify what is really the intrinsic change, separated by all other changes. In addition, muscle fibers are not all equal. So with the study at single fiber level, we can also separate different fiber types and see which fiber type are more responsible of the deterioration of the muscle during aging. Muscle fiber studies are rather demanding studies because there is not yet a robotic hand which can take out individual muscle, single muscle from a biopsy. You see in the panel a typical example of what we see under the microscope when we take a biopsy from a human muscle. There is no robotic hand to take out single fiber, put them in a setup between a force transducer and a motor, and measure all the... About measuring, yes, we are rather close to have some robotic help, but anyway, so there are some machine who can perform almost completely an experiment, but at least some part of the work needs still to be done by hand and is demanding and time-consuming, but still worth to do. Worth to do because when we have in our hand a single muscle fibers, we can collect a lot of different data. A lot of different parameters can be measured. Here I make just a very schematic list. Of course, we can measure the size, the thickness, the cross-sectional area, the sarcomere length, structural parameter. We can measure mechanical parameter of the contraction, how much force, shortening velocity, power, and so on. We can measure energetic parameter of the muscle contraction, how much ATP is consumed, what is the efficiency. We can, from the single fiber, take out some molecules, separate them with electrophoresis and identify with Western blot. We can do on the small sample histochemist and immunohistochemist. We can do some biochemical reaction to test some enzyme activity. And more recently, we can also apply to single muscle fiber omics approach. So in a small segment, few millimeter long of fiber, we can identify thousands of transcripts and thousands of proteins with the omics techniques. We must always remember that we cannot study excitability because, so to say, a precondition to work on single fibers is that we destroy the sarcolemma, either chemically, permeabilization with tritone, saponins, or mechanically, just peeling out the sarcolemma. But excitability is something which cannot be really studied with single fiber dissected from a biopsy. About the mechanical parameters of single fiber during aging, a few months ago, Gorski and his collaborators then published a beautiful review article on journal Physiology. Beautiful review article where they collected very carefully 27 studies. Among them there are also our studies, Roberto Bottinelli in the first place is one of the list. 27 studies on single muscle fibers from 97 to last year, 22, over 25 years, and reported comparative. The old are the filled circle, the empty circle are the young, the blue are the men, the red are the women, then the green and something else. I don't remember what is the green. Anyway, many different studies well classified and calculated averages, comparing cross-sectional area, isometric force, isometric tension, shortening velocity, calcium sensitivity in all these people. So in a way, all results available are here. But I don't want to discuss this. I prefer to move to my personal experience. Also because if I make a criticism, they didn't take care of the different phases of aging. So we cannot put together really a 90-year-old person and a 75-year-old person. There is a difference, as we will see. So I present 3 of my works now. The first was a comparison between 7 young donors and 16 older adults. I cannot say that really elderly people. The average was 60 years. So we were at the edge between adult age and old age. Anyway, a difference in age is sufficient to produce a clear difference in performance and mass of the muscle. The muscle studied, considering all these 3 studies, is leg extensor muscle and biopsy taken from vastus lateralis. So here the volume of the muscle is significantly different, significantly lower in the elderly or older adults compared to the young, and the power, the peak power, again an explosive ergometer to measure, is significantly lower. So there is an effect of aging. An effect of aging is present at all muscle. Then we go down to the single fibers. The size of the single fiber, the slow fiber are just the same. The fast fibers show a clear indication of atrophy. They are significantly thinner. We measure the force, we divide the force by the cross-sectional area. P naught, that is the isometric tension normalized for the size, is not changed. So the slow fiber is just the same as in the young. The fast fiber are thinner, but their intrinsic ability to develop force is preserved. And the same way is preserved the maximum shortening velocity, which is in the diagram here. Second study. In this case, the donors were a bit older. So we had 4 young men and 4 elderly men, 72 years the average age. So we are at the border between older adult and old. We measure the maximum voluntary contraction of the leg extensor muscle. Again, a clear, significant difference. Rather pronounced, I must say. Not 50%, but almost 50%. We go down to fiber level, to single fiber level. No difference as to the size of the slow fibers. Again, pronounced atrophy of the fast fibers. So more or less the same observation that we have done with 60-year-old fellows. And isometric specific tension is preserved. So the fiber works well. They are not damaged, they are not impaired in themselves, but they are thinner, they have become atrophic. With the third study, we could move up to the oldest old. We had the possibility to find some women as donors, so we had 8 young women, not specially trained, rather sedentary girls, and 16 elderly women, average age more than 89. Some of them were still able to walk, and some of them were confined on the wheelchair since some years. Here on the left side, we see the measurement of the leg extensor muscle in vivo. So the atrophy is rather impressive. More impressive for the not walking, for the women confined on the wheelchair, but even also more, very much pronounced in the still walking women. The maximum voluntary contraction was tremendously reduced. even when we normalize to a physiological cross-sectional area of the extensor muscle, like extensor muscle, there is still a significant reduction with aging and with inactivity. Well, we leave out now for the moment inactivity, but anyway, in these very old people there is pronounced loss of muscle, pronounced loss of force. We go down to the biopsy, to the single fibers, and in a way, to our surprise, the situation is not very different from what we have observed in younger elderly people. So, slow fiber are not atrophic, even not significantly, but even the average is a bit higher in the elderly women. Very pronounced is the atrophy in the fast fiber, but surprisingly more in the 2A fiber than in the 2A, 2X fiber. To have pure 2X fiber is very different, very difficult. It's very difficult to get a number of pure 2X fiber sufficient to make a statistically comparison. If we look at the histochemical, immunohistochemical section, staining of a section of a muscle, we can see just very high a difference. Of course, this is a bit selected example, but here the only staining is in green, the slow fiber stained with an antibody against slow myosin. So if you compare the young and the old, you see that there is a big change in the proportion of the fibers. There is a big increase in the number, in the proportion, in the percentage of slow fiber, which is also visible here in the histogram report, in the average of the 9 or the 8 people, not the mobile people. So there is a decrease in the percentage of the fast fiber and increase in percentage of the slow fiber. So there is not only atrophy of the fast fiber, but disappearance of the fast fiber, particularly the 2A fiber. So from this I started to wonder what is the next change and what is in which direction is going the deterioration of the muscle in this so advanced age. Definitely the muscle continuously go down, the quality, the performance, the mass, everything goes down. But the changes that, for example, of the slow fiber are not very evident. And the changes of the fast fiber are more or less the same as we have seen in 60 years old people. So maybe the most important factor becomes the disappearance of the fast fibers. And so he went back to consider all the studies, classical studies of Lexell in the 80s of the last century. Our group, 3 groups of elderly people are more or less located here. This is the age. This is the total number of fiber in the quadriceps, 1 million fiber. This is 1,000 by 1,000, 1 million. So after 40 years, the number of fibers start to decrease, and there is an acceleration with this decrease, which corresponds to the disappearance, the death of the motor neuron. Well, I think my interpretation is that the atrophy of the fast fiber is a continuous process, but the disappearance of the fiber, particularly the fast fiber, becomes at a given point, when we arrive here in the oldest old, becomes the most important component. So there is a different balance between the two phenomena. No? The death of the fiber, the disappearance of the fiber becomes more and more important going further with aging. This is another original beautiful diagram of Lexell 30 years ago. So the question was then if we can understand something about what happens in these fast fibers during their aging. And for this reason we take advantage of the proteomics approach, which could be developed at single fiber level in collaboration with the Max Planck in Munich. So with their powerful tools, we could get from a piece of fiber long with a length of a couple of millimeters, thousands of proteins identified and quantified. If you look here in this, histogram, each segment is a fiber, and this is the number of fiber identified, number of protein identified in that fiber. The average is around 2000. So 2000 protein per fiber had been a segment of fiber identified and quantified. Not in all fiber the same protein. So in reality we could measure, we could quantify 4,000 proteins both in elderly and young subjects. Our donors were the same I mentioned in a previous slide, so 4 young men and 4 elderly men, average age 72. On the all 150 fiber were studied, and they were classified in slow and fast fiber depending on the expression of the myosin heavy chain isoform, or at least of the expression of the predominant myosin heavy chain isoform, because with such very powerful analysis of the protein composition, we discovered that almost all fiber express more than one, generally 2 isoforms of myosin heavy chain. But we put a threshold at 80%, so if a fiber expresses, for example, more than 80% of myosin 2A, myosin 2, then we can classify as a fast 2A fiber. No? So we formed 2 groups and we compared the 2 groups. We compared the 2 groups and we used gene ontology and our bioinformatics tool to classify, because you cannot really by hand divide 2,000, 3,000 proteins and put them in order. So we need some bioinformatic help. The result showed that, for example, the metabolism had some significant variation with aging in slow and in fast fiber. Of course, the metabolism, we don't measure the metabolic activity, we measure the quantity of the enzyme. We can make an assumption, which is rather acceptable, I hope, that enzyme activity is proportional to the concentration of the protein enzyme, assuming that the rate constant of the enzyme is not changed with aging, which is not completely sure, but is a reasonable assumption that there is a proportion between activity and quantity of the enzyme. So some of the changes were definitely expected. For example, the decrease of the mitochondrial proteins. We could identify almost in all fibers all proteins of the Krebs cycle, all proteins, almost all proteins of the OX-phos chain, so the 5 complexes. Here you see, just to choose one of the 2, I put here some kind of summary of the data about the OX-phos proteins. The blue is the symbol we use for slow and green for the fast. Going down means the decrease, of course, so all 5 complexes show a decrease in the abundance of the protein, which is an indication, together with the decrease of the Krebs cycle enzyme, that the mitochondria are less present in the elderly than in the young, which is not new, has been described already since a couple of decades at least. But anyway, it's an important point, because it means that there is some kind of energy deficit in the elderly. But on the other side, some surprising results about the glycolytic pathway. The glycolytic pathway is more developed in the fast fiber than in slow fiber in humans. Maybe not in mice, but in humans, yes. Well, to our surprise, the fast 2A fibers show a decrease in the abundance of the enzymes of the glycolytic pathway, and a decrease of the enzymes of the glycogen metabolism. Again, blue and green represent fast and slow. In this case, leftwards means decrease, rightwards means increase. So there was an increase in glycolytic enzyme in slow fiber in the elderly compared to the young, and a decrease in the fast fiber. One could say, with extrapolation, that the slow fiber compensate partly the loss of mitochondrial impairment with developing the glycolytic metabolism. The fast fiber lose both. So there is a more pronounced energy deficit in fast fiber than in slow fiber. This can be one of the reasons behind the atrophy. Then another point, which was rather interesting, is about the proteostasis, the balance between synthesis and degradation of proteases. Also here we could identify several proteins involving ribosomal activity, in proteasomal degradation, autophagy, and some chaperones also. Again, the symbols blue and green are slow and fast. Again, leftward decrease, rightward increase. What we could observe that slow fiber, the blue, showed a general increase in the abundance of these proteins. So, if there is this relation between abundance of protein and function, this means that there is increase protein turnover, more synthesis in the ribosome, more degradation in the proteasome, more autophagy, but also more folding by the chaperones. For the fast fiber, didn't occur. So also this level, the fast fiber were more in difficulties than the slow fiber, and this can be another component of the decline, intrinsic decline on the fast fiber. So now I'm going to the conclusion. Say that single fiber study is demanding. I've been doing for many, many years, and I know how much is time-consuming and also sometimes tiring. No? Dissect single fiber one by one, take piece of fiber one by one, takes a lot of time and work, but still is useful. It's useful because we can get some interesting and unique information. From what I could show now, I can take some conclusion. First place, that there is an intrinsic aging of fast fiber, atrophy and proportional loss of performance. Proportional, so the isometric tension, for example, tension is preserved. No? There is an impairment specific of the fast fiber, atrophy and loss of performance in proportion. Slow fiber withstand much better the aging. This intrinsic decrease of the quality of the fast fiber is responsible for part of the muscle decline. But another important part is the disappearance, the loss of the fibers. And this second component becomes more important than the first one in the oldest old. The single fiber proteomics has opened some little windows, just some, it's not completely clear, what can be the metabolic alteration responsible of the atrophy of the fast fiber, no? The energy deficit and the altered proteostasis. And with this, I'm finished, and I thank you for attention. Well, for the first question, it's a matter of the development of proteomics. No? I mean, the type of the proteomic, I'm not the person doing this. No? As you know, I know what type of work I do. It's just the person dissecting. But, the type of proteomics approach followed at the Max Planck Immunity doesn't see any post-translational change. So you don't see if they are phosphorylated, glycosylated, so you don't see anything of this time. So this is definitely a very important point to understand if there is some effect of these glycosylations. I know that there are other labs which can do, for example, a phosphoproteomics. No? So at least for protein phosphorylated is possible. But the studies we have done, and also you have done, don't consider at all the phosphorylation and the post-translational modification, which is still a rather open question, this. No? The second point is also very interesting because it has two sides. One side is that when we dissect the fiber, very likely we make a selection, no? Involuntary. No? We have there thousands of fibers, so we must take one. So which I take the best, the most beautiful, So this is a very worrying point. No? Also the review by Krosinski and co-workers in Physiology discussed this point, the problem about involuntary selection of fibers. So this is a rather interesting question, no? To see if we could compensate in some way for this. Definitely I haven't done myself. But about the contribution to the force of the denervated fiber, I think that they don't contribute, so they really disappeared. You know? So from the functional point of view, they don't exist. But of course, it would be very interesting to see, for example, their metabolic condition, to see something of their size. This we cannot do in single fiber studies. We can only do in sectioning and taking.
Yes.
A wonderful talk. Thanks, Carl. So, question. One of the things that happens with denervation, so building on what we've just heard, is you get a switch in myosin heavy chain isoform expression. But it doesn't lead to a complete alteration of the proteome. So, if a type 1 fiber becomes denervated, gets reinnervated by a fast motor unit, and switches to a fast fiber, it still retains some residual echo of its original type. And the opposite is true as well. So I wonder, to what degree does our understanding of what's changing in type 1 versus type 2 with aging, is it compromised by not knowing the history of individual muscle fibers? So have they always been 2, or have they always been a type 1?
Yeah. Good point. That is a good point. The history, it's true that we take a picture, no? We take the picture of the family and we don't know how when people were children. That is a good question, yes. So when we say, for example, the fast fiber has lost their metabolic activity because their glycolytic activity, because maybe they were, in the past they were slow fibers. No? Good point. This is something to think about. While the question by were rather expected, this is a really good point, to think about the history of each fiber, one by one.
Thank you. Very interesting. A lot of possible question. One, a very general one. So the fast fibers go through alteration in metabolic energy supply and proteostasis, as you say. Do you think this is intrinsic to the fiber type, or depends on the innervation, and so from a change in the motor neuron that control them? So, do you think there is something that comes from muscle that affects neurons, or that the selective impairment of fast fiber depends on a phenomenon that occurs in motor neuron? Because it is very discussed, so and maybe you have a point of view on that.
It is a very interesting point. Because the fast motor neuron, the big motor neuron, die before the small and slow motor unit. If this is a consequence of the cause of maybe Marco can say something about this. No, but it's a very interesting point. This because, you think that the motor neuron are the master of the fibers, but in reality, without their fiber, the motor neuron die. No? So it can be really something coming from periphery to the center.
Yes, we still have to understand a lot of the crosstalk between the motor neuron and the muscle.
Thank you.
Carlo, I have a question that you may already have answered, but which I may have missed due to old age. I like to think it's because my hearing is not what it was, rather than a cognitive decline. But anyway, here is my question. So the loss of fibers, muscle fibers, that you see with old age, is it all due to loss of motor neurons, or is there some intrinsic loss in the muscle fibers independent of what happens to the motor neurons?
Yes. Well, this is in a way related again to the question, where starts, from the periphery or from the center? No? If you start from the periphery, if the fiber get old and degenerate and deteriorate by themselves, and then the motor neuron die, it's possible. Let's start from first the fiber and then the motor neuron. That is possible. But there is anyway a close relation, because Lexell measured fibers motor axon and motor neuron in the people at the autopsy. No? So you could see that it's proportional. No? So you see that the fast fiber disappears, but also motor axon for the fast fiber, which are thicker, disappear, and motor neuron, big motor neuron, disappear. So there is a strict relation between the two. But where start, that is a difficult question to say. I think that would be very important also to understand the possible countermeasure. If you can slow down this process, it would be very important to understand if we start from periphery or from the center. Definitely all neurons die, no? All neurons die. Every day in our cortex, thousands of neurons die. But in our cortex we have billions of neurons, and it's not a big problem, or a little problem, say. But the motor neurons are not so many. A few thousand, few tens of thousands of motor neurons. So when we lose one motor neuron, it's something that cannot be really recovered. No? So I could imagine that motor neuron dies just as the same processes, oxidative stress or other things, as in the brain cortex. But the impact of this disappearance of a motor neuron involved hundreds of muscle fibers and is a bit almost irreversible. No? That is a very important point.
I think we have one question.
Yes, you pointed out correctly that different approaches have limitation, like, for example, the single fiber approach. And I think we need to collect information from many different approaches to get a full picture. And one new approach is the single nucleus RNA-seq, which has the advantage of collecting information from, in principle, all myonuclei without the possible selection you were referring to. Obviously, you see only the transcripts, not the protein, but still, this could give information about denervation events, for example, that take place at various myonuclei. So I think that this, as far as I know, there is no study on single nucleus RNA-seq during aging.
Yet, we are doing that.
There is one. There is one. There is one. There is one study about nucleus RNA-seq in the aging, I think.
In animals.
In animals.
In
I think,
animals.
in animals.
We're doing it in humans. We have one question?
Short question, but I just really want to give the mic to the young people. Any of the young folks want to ask a question? We had a lot of senior people ask questions. But after me, a young person needs to ask the question. I was just wondering about the single fiber proteomics. If this was done, the proteomics was done in that specific single fiber, or was it done in a bundle? And then maybe handed off to a younger person.
Was done in specific single fiber. So I dissect the fiber, put the fiber in a vial, in a append vial, and then in that append vial was all the digestion, which is tryptic digestion. Single, each 2 millimeter, 3 millimeters long segment, and then from that everything was done.
But again, if you do repeat measures in a different fiber, would you get the same results? Have you done some comparisons? You see what I'm saying? Because they could all age slightly differently.
You mean 2 pieces of the same fibers? Yes, we have done something. We have done something to see how much was the difference in, and I mean, is other reproducible, at least. What I mean is that we take 5 millimeter fiber, I divide it in 2 pieces, 2 millimeter and 3 millimeter, put into append vials, and yes, we have rather similar results.
Any question from the younger audience? Please, don't be shy.
Marco, there is one here.
I'm not sure I'm still in the young age. I was just wondering, related to the question on single nuclei, if you've looked at the RNA level, if all the change that you see at the protein level, do they correlate with the same change at the RNA level? If you've done any, have you correlated to the question on single nuclei study? Have you looked if the change that you see at the protein level are correlated to the same study at the RNA level? You don't know.
Unfortunately not.
Okay.
That would be something nice to do. I mean, surprisingly, there are studies on single cell, single muscle fiber, transcriptomics, omics approach in mouse, but not in human.
Yeah.
And our studies, well, I mean, because I think it's more interesting, was done in human, also because of the approach to the human physiology. That would be something to do, and not so difficult with the present-day technique.
I have to move because I take this opportunity to thank one of the co-authors, without the name, in this bad book, Ugo's book, that I decided to write, so heavy, because I decided to collect CV from many colleagues. And one of these was Carlo. When Carlo accepted, I started to write the book. And therefore, please.
Ugo's Bible.
It is a common propaganda.
Thank you, Ugo.